This is question number 17 in Giancoli chapter 19. The question has a circuit drawn that I've copied, and it reads, determine A, the equivalent resistance of the circuit shown in the figure, and B, the voltage across each one of the resistors. I've made the sketch here, and we should easily identify a couple of nodes in the circuit giving away parallel branches. So I've got node A here and node B. And attacking these problems first involves finding the equivalent resistance of the parallel network, which I will cloud here in green. So those two nodes should give away that parallel network. I'm now going to use my standard equation for equivalent resistance for resistors in parallel. 1 over Req is equal to 1 over R1. In this case, that's 820 ohms plus 1 over R2, which is 680 ohms. That's going to give me 1 over my equivalent resistance. And therefore, once I find the reciprocal of that, I'll get 1 over Req is equal to about 372 ohms. So I can effectively treat these parallel resistors as if they were a single 372 ohm resistor. So I've kind of drawn that in here, but you can leave it without that additional green resistor. That's not the total resistance of the entire resistor network. In this case, it's a combination series parallel, so I can say that the equivalent resistance of the 372 ohms is going to be added to this 470 ohm resistor, and so therefore the total resistance is going to be 372 ohms of the parallel plus the 470 ohms that it's in series with, which is going to give me about 840 ohms. That's our answer to part A, finding what they call the equivalent resistance, but what is really the total resistance of the entire circuit. I reserve the word equivalent to talk about parallel networks. Part B says find the voltage dropped across each resistor. In order to do that, we first need to figure out what the total current is in the circuit. I can do that by applying Ohm's law broadly or globally to the entire circuit. So I'll say that the total voltage is equal to the total current times the total resistance, which I've now found in part A. So finding current, it's going to be total voltage over total resistance in the circuit, and that's going to be the total circuit current. And I'm going to get 12 volts, which is my battery voltage, divided by the 840 ohms that I solved for in part A. And I'm going to get 1.425 times 10 to the minus 2 amps, or 0.01425. 0.01425 amps will be the total current that's being supplied by the battery. I could call that 14 1/4 milliamps if I wanted to. Either way, I'll leave it as that. That's not what I'm looking for, though. I do know that that's the current here that I'm going to show in red. And then as soon as I hit node A, I get 2 branch currents that I'll denote by these dashed lines. Those 2 branch currents recombine. This is conservation of charge, law of nodes. The sum of the currents entering the node is the sum of the currents exiting the node. So I again have total current flowing through that 470 ohm resistor and then back to the battery. Using that, I now know the current here flowing through this 470 ohm resistor, so I can use Ohm's law directly across that resistor. And so I'll do that in the second part of B. I'll say that the voltage dropped across that 470 ohm resistor is equal to the total current times its resistance. In this case, the total current is the 0.01425 amps. And I'm going to multiply that by its resistive value of 470 ohms, and that's going to yield a voltage drop of 6.7 volts. So now I know that there are 6.7 volts dropped across this resistor right here, and via the law of loops, which I'll do with this purple line, I can see that I've got one loop right here. And in that loop, the sum of the voltages lost and gained needs to be 0. So if I gain 12 volts right here at the battery, and I lose the 6.7 volts across the 470 ohm resistor, that means that the balance, or the 5.3 volts, needs to be dropped. Yikes, that's not writing properly. 5.3 volts will be dropped across the 680 ohm resistor. So the voltage dropped across the 680 ohm resistor is 5.3 volts. And by nature of these nodes, point A and B, these are parallel legs, and that means that the same voltage is dropped across the 820 ohm resistor as well, also 5.3 volts. I could see that separately using a separate loop here, which I'll draw. If that purple loop is the first loop that I drew from the battery, I'll draw a blue dashed line, and here is my second loop. And if I follow that line as well, I'm going to see that I again lose the 6.7 volts here, which means that the 5.3 volts needs to be dropped across that 820 ohm resistor. That's using the law of loops, or conservation of energy, to basically answer alternative ways of answering part B.